Hey everybody, we're going to start our first section. You'll see me down in the corner. I hope I don't cut off too much, but this is the book you need to get. You'll get it at the bookstore, An Introduction to Chemistry. And again, it's real basics of it. Don't worry that if you haven't had chemistry before, you'll be fine. You can get through this. So we're going to talk about really what is chemistry. Chemistry is the science of matter. And you're like, matter? Matter is everything you can touch, see, or feel. So if it's matter, you study it when you're a chemist, okay? Matter has a mass and occupies space, all right? So if you can touch it, you can see it, you can feel it, it's matter. Now, once in a while I'll ask people, okay, tell me something that isn't matter. And some things come up and people will say like air. That's the most common. You ever been outside on a windy day? I'm sorry, but you can feel air. So air is matter, okay? Chemistry, if you're a chemist, what you do is you deal with matter. What it's made out of. Is it made out of hydrogen and oxygen? Is it made out of nitrogen? Whatever. It's structure. Okay, structure is very important in chemistry because it determines a lot of things about that object. The properties, how does it react? Who does it not react with? And this is really important if you think about it. Aluminum is a great substance, great metal because it doesn't react with very many things. So we really appreciate that property about aluminum. And again, when you react it, what kind of stuff do you get from it? Do you get a lot of energy from it? You know, when we put gas in our car, we burn gas, it gives us energy so that our car moves, and we'd be kind of in big trouble without that. So there's all kinds of things that chemistry deal with, but really anything you touch, see, or feel, that's what, if you're a chemist, that's what you study. Excuse me. Chemists devise experiments and to see reactions. They take data and they interpret it, and then they try to make new substances. And we're going to look at some of this. I know because of our strange situation with the lab, I might have to do some of the stuff, show it to you, give you the numbers, and then you guys are going to have to make sure that you understand the data. That's how we'll interpret it. Okay? Chemists try to understand how and why chemical changes occur in the human body. If you really, really want to get into a big field of chemistry, you can become a biochemist. And a biochemist studies biology and chemistry, biology of living, or the chemistry of living things. Now you might think, wow, well, if you're a biochemist right now, do a lot of work with DNA. They're the ones that discovered how to sequence it, and think of the huge, huge deal that's made in our life. We've been able to cure diseases. We've been able to assure paternity. It's in forensics. It's everywhere, and DNA is huge, and that's what a biochemist would have done. Okay? When you're a chemist, we look at the macroscopic world, which we can see, and we look at the microscopic, and a lot with chemistry is microscopic. Okay? Microscopic, in other words, when we work with chemistry, we talk about atoms, we talk about molecules. You cannot see them. Actually, they do have some really cool microscopes that can see atoms and molecules. Oh, we don't have any of those. It's not your standard little compound microscope. It's, serious. So you can see up here, we have the water, and if we analyze the water, here's little water molecules. We got some oxygen. We got some salt particles. You got all kinds of things in there. Okay, so as a chemist, we'd analyze this to see what particles, what atoms and molecules are in there. Okay, so if you hold one molecule in your hand, what would it look like? Well, if you think about it, molecules are so tiny, so tiny. So for you to look at it, it would be, you'd have to have a pretty fancy microscope. Pretty much everybody knows that water is H2O. What does that mean? It means that's 2 hydrogen and 1 oxygen. A molecule of, now I'm talking pure water, you guys. I'm not talking about the stuff we get out of the tap. Because remember, the stuff we get out of the tap is got other stuff in it. It's got iron, it's got calcium particles, it's got sodium. And the way I can tell that is water from Botno, where I live, is way different than water from Belcourt. There's different particles in there. They don't taste the same. There's all kinds of changes you've got. So I know that's not a pure substance. It's not pure water. Water, like distilled water, H2O, 2 hydrogen, 1 oxygen. Okay, and there you have it. They call it the Mickey Mouse molecule because if you look at it, the hydrogen kind of hang out together, and then the oxygen's down the middle. The oxygen's always in the middle, and the hydrogen are attached to it. And again, They call it the Mickey Mouse molecule because you got this guy going on there. Okay. When you're a chemist, honestly, when you're anything, if you're trying to solve a problem, use a scientific method. Now, you might not think you use a scientific method because you don't really like science, and it's like anytime you solve a problem, use a scientific method. It's a logical approach. If you're trying to do something simple like figure out why your car didn't start, using the scientific method, okay? And most of us, let's face it, we just call somebody and have them help us out. But the scientific method is a process we use to solve problems. And it doesn't have to be a science problem. It can be any problem, okay? When you have the scientific method, you collect facts and you collect data that's relative to your question. Number one, you have to have a problem. Let's say you're sitting outside and you notice that these birds are flying into glass, into windows. It's like, that's really strange, what's going on? So the first thing you'd have to do to use the scientific method is you'd have to say, why are those birds flying into the windows? If you don't have a problem or if you don't have a question to answer, the scientific method is useless because it's used to solve a problem. So once you have a problem, then you're going to collect facts, data relative to your question. Okay? You're going to perform an experiment, look at your results and see. And again, it doesn't have to be a big scientific, solve cancer or whatever. If you're looking at those birds, you might walk over and see that there's some berries that they've been nibbling on. And then you do a little research on those berries and you find out, oh, wait, they're fermented berries. So basically, the birds are, hammered. They're drunk and they're not flying the way they should and they're running into things, something like that. Okay. Once you have your problem, you've done some background, you got some information, now you form a hypothesis. And I know most of you guys, when I say hypothesis from your elementary training, you're going to say, oh, that's a scientific guess. It doesn't have to be a scientific guess. It's your guess on what happens. Hopefully it's an educated guess because you did this stuff up here. But a hypothesis is a tentative explanation. It's what you think happened. Okay, and if you really want to write a good hypothesis, you should say if and then. If this is the case, then this will happen. If those berries are causing the birds to, be drunk, then the more berries they drink, the more likely they are to run into the windows. Stuff like that. Okay, that's a hypothesis. And then you're going to design an experiment to test your hypothesis. You're going to figure out how, I don't suggest that you go eat the berries to see if you get drunk and run into the windows, but you know what I'm saying? You could do some sort of test on the berries to see if they have alcohol content in them. Okay? And then again, make sure your hypothesis is a good hypothesis. Sorry about cutting it off, and I haven't found a spot where I can put myself, so this is the best I can do. But again, your hypothesis, you use an experiment to test your hypothesis. Okay? When you're done, you have data. Okay, so you test the berries. You check them out, and sure enough, they're fermented and they have a little alcohol content, and you observe the birds eating the berries. Okay, so you got a reasonable, you can draw conclusions from that. If you're, really good on your experiments are really well done, you can come up with theories. Theories have come from hypotheses that have been proven over and over. So they say a theory is a valid hypothesis, but it says there, no evidence to disprove them. There have been theories that have been disproved. My favorite is the theory of spontaneous generation. They used to think that worms came from rain because every time it rains, there's worms all over the ground. So they thought worms could come from nothing, or, that was spontaneous generation. Well, it took them a little while to realize they soaked the ground and the worms had no place to go. So there have been some that have been proven wrong, but there are still some theories out there. It depends. Okay? There's also laws, and laws are based on natural phenomenon. There's not exceptions. If you've done physics, Newton has the law of physics. There's 3 laws of physics. So there's the difference between a theory and a law. A law is a natural phenomenon. There's no exceptions. It's not going to be proven wrong. A theory is somebody came up with an idea, they tested it, and now it's, it can be proven wrong. So there's a little difference in a theory and a law. Okay, so when we're talking about matter, remember, if you're a chemist, you study matter. Matter appears in both forms. It's big, it's small, it's huge, it's little. Okay, and when we do chemistry, we talk about atoms. Atoms are the smallest particle. Okay, and here's an example. I was telling you we don't have a very fancy microscope at the college. This would be an electron scanning microscope. You can actually see atoms. It's pretty cool. They're pretty tiny, and we'll talk more about how many atoms we have later. But these little atoms tell you everything about that matter. It tells you what it is. It tells you what elements you have, how much of those elements. It tells you their phase, which we're going to talk about. See, when they're really close together and they can't move very much, then you're probably going to have a solid. Okay, when you spread them out a little bit and they can slide across each other, you got a liquid. And if they're really cruising apart, then you've got a gas. So these little tiny particles, we call atoms, give you all kinds of information about that substance. Okay, and again, the three physical states of matter is a solid, a liquid, and a gas. And I'm sure you guys have heard about these before. I'm pretty sure in elementary school it was one of those things you like to do. But again, a solid is defined as a definite shape and volume. Why does it have definite shape and volume? Because of those particles. Those atoms are so close together. Now, some people think they don't move. They do. They just kind of wiggle back and forth. Okay, they don't move real heavy duty, but they do move. Okay. Common solids are the crystalline, where they're really, really tough. You know, here's showing you ice, where the particles are really stuck together. That is why we call it a solid, again, because it's shape and it has a definite volume and shape. Okay. We also have solids that aren't so much like that. Plastics, glass, gels, they're called amorphous. If you think of like silly putty or slime, you know, everybody, little kids' favorite thing, those are solids, but because they're not a set crystalline shape, they're called amorphous solids. In other words, they can change their shape, which is kind of different for a solid. Okay, so we do have two types of solids. When they're really tight and stuck together, that's crystalline. When you can spread them out a little and they can change their shape a little bit, that's amorphous. And again, think of silly putty, think of slime. Those guys, they're solids, but they're not, you know, they don't have a set shape. You can change their shape. And again, a liquid, the particles aren't too much farther apart than they are in a solid. But because they can slide across each other, then they can move more freely. So a liquid has a definite volume, but it takes the shape of its container. Okay, so if I have two different types of beakers and I pour 50 milliliters in each, they might look different. They might have a different, you know, shape or size, but the amount, the 50, is still the same. Okay, and then the last one is a gas. And we actually spend a whole chapter on gases because gases are special. They have a lot of unique stuff going on. They have no definite volume, no definite shape. Gas particles don't like each other. They spread out from each other as far as they possibly can. Okay, so they'll fill a container and they'll do that. They can be compressed, they can be expanded. When you change their temperature, they move faster. When you heat them up, when you slow them down, you can change pressure with them. There's all kinds of things you can do with gases, and you can't really do that with the solids and liquids. So the gases are pretty special. Okay, so now we're going to take, I got to quit here because I can only do 15 minutes at a time, you guys. That's all you get from me. What I'm going to do is I have some, in the next part of you'll see in the module, I have some questions for you to go through about the scientific method. So I'm going to have you do those, and then we'll come back and I'll have recording for the rest of this chapter. So this is chapter 1, the introduction. I got to break it down into 2 because I talked too long. Sorry about that. But again, work on these scientific method problems, and I'll talk to you later.